Hello, Fruitport High School students and staff. I'm trying to make a series of videos as we start our new thing on stoichiometry. And there's two ways that we can teach stoichiometry. One is using dimensional analysis, and another is using BCA tables. So you're going to learn dimensional analysis through textbooks, and you'll learn BCA tables through what we're doing here, through me, and through some lessons. So we'll just do a couple of these and stop along the way. So uh, so if you're in class, we'll do this together. But if you miss class, we're going to get this packet here, an introduction to stoichiometry and BCA tables. And we're going to practice using these. And I'm going to try to model all my thoughts and steps. I'll try to use colors to make it nice too. But for each of the problems before, you're going to need a balanced chemical equation. And then we're going to read the question to figure out what's given to us and what do we want to find. What's the question asking for? And this is the first time that we're going to actually study the coefficients from the balanced equation, and they'll be in moles. So I'll just kind of show you how this works, and let's see if we can learn from this. Okay. So we have this little paragraph that we'll read in a second, and we have the BCA tables. And BCA tables stand for before, change, and after. And this is tracking the moles of every substance before, the moles that are going to change, and the moles that are after the change. And they're kind of lined up. So like oxygen will be documented here, and sulfur dioxide will be in this column, and water will be in this column. And so one of the things that we're going to learn in BCA tables is that the before and the change always add up to equal the after. And we also are going to always know that these, whatever numbers we put in this table, can only be in moles. It can't be in molarity. It can't be in grams. Moles are the preferred units. Okay. Now, the whole point of stoichiometry is we're studying the balanced equation. So we need to balance this one. This one's not the easiest here. When I see two hydrogens and two hydrogens, I was pretty happy. And one sulfur and one sulfur, I was pretty happy. But I got this odd oxygen total on this side and the even oxygen total on this side. So I think we're going to have to double the hydrogens in this situation here. I'll have 4 hydrogens and 4 hydrogens now. This gives me 2 sulfurs, but I don't have 2 sulfurs on this side, so I'll put a 2 here. And I believe now this is 4 oxygens plus 2 more oxygens, which is 6. So I'm going to need 3 oxygens over here. Okay. So the reason we balance the equation is that the coefficients, which I'm doing in red, I'm going to put a star on the change column because the changes are going to have to be in a 2 to 3 to 2 to 2 ratio for this equation. All right, this recipe, so to speak, is showing us what you start with and what you end with. Okay. The next question, I'm going to read the question. Hydrogen sulfide gas, which smells like rotten eggs, burns in air to produce sulfur dioxide and water. How many moles of oxygen gas would be needed to completely burn 8 moles of hydrogen sulfide? So it looks like they're asking how many moles of oxygen gas are needed. That's going to be this box right here. We want to know how much oxygen is required to start this reaction for the reaction to work. And they give us this fact. Let me use a different color here. Let me use pink. They give us 8 moles of hydrogen sulfide, which means that we're going to put in 8 right in this box here. I'll underline it. And I'm going to use I guess I'll use a pink marker. You should be able to see 8. We're going to put an 8 here. Now this means 8 moles. And after a while, I'll stop writing the units down because we'll always know that they're asking for moles, the whole BCA table. So I'll put a little question mark there. That's what we're solving for. Okay. Now, in this situation here, how do we figure out how much oxygen is needed? Well, some of you might be trying to do this in your head, and that's great, but the power of the BCA table is where I really like to go for this. I'm going to use the green marker to show the thoughts here, okay? And so here it says we're going to completely burn 8 moles of hydrogen sulfide, which means at the end, in the after, there's 0 moles of hydrogen sulfide left over. Okay. So in order to get from 8 to 0 with this phenomenon that the B plus the C always adds up to A, it's kind of like you're solving for X. 8 plus what equals 0? And the correct answer is negative 8. 8 plus negative 8 equals 0. So as we move down the column, remember the B plus the C always equals this A. This negative 8 means that the change of moles is we're going to use, that's what the negative means, we're going to use up 8 moles. Okay. Now, in order to work up to this one here, we're going to have 0 moles here. This is the key maneuver right here. This number is going to be negative 12. You might be wondering, where did you get that, Mr. Kobe? Like, how'd you get that number? And the answer is that the change numbers are always based on the ratio. And so I had to pick a number that has the same ratio as a 2 to 3 ratio. Um, you could look at it like fractions. 2 over 3 equals 8 over x. And I solve for x. I guess it's negative 8. And then I would end up with the 12. However you want to come up with this, you're going to have to use some math proportions, math ratios, math logic to figure out that this 8 and this 12. If you're struggling, what you do is you just 8 divided by 12 on your calculator. Let me clear this out. Clear, please. 8 divided by 12 equals 0.666666, right? And 2 divided by 3 also equals that 0.6666. Okay. So now I have to do this. What plus negative 12 equals 0? And the answer is 12. Remember, the B plus the C always equals the A. Now we're technically done with this problem. We've solved it. Now, just to show you why did we do the whole BCA table here? Why do I have products if we're not even going to use those? Well, we could continue. If there was a second question like, well, how much water do you make, or how much sulfur dioxide, we'd end up with a 0 here because we start with 0 moles of our starting material. And I'm going to put a positive 8 and a positive 8 here. The reason that this number and this number are both 8 is because the coefficients are the same. 2 to 2 ratio is the same as a 1 to 1 ratio, or the same as an 8 to 8 ratio. The other thing we're going to learn is when you're on this side of the arrow, the product side, you're always going to have a change of increasing because you're literally making new chemicals. So the change has to be positive. This side of the yields arrow is the reactants, and those changes are always going to be negative because we're using those up. So as we use them, the amount goes down. And again, the B plus the C always equals 8. So we'll get 8 moles and 8 moles. Now, this would complete the entire BCA table, which for our first problem is a little bit unnecessary. I don't even think we need to do this boxes or these boxes because the problem is referring to only how much oxygen gas would be needed. But in the future problems, we'll use all those. All right, so I hope you enjoyed this first level 1 problem. I'm going to hit stop and save it and then record a couple more for you.